Howdy there, folks. How about we do a proof of Euler's formula, proving that e to the I plus 1 equals 0, aka Euler's formula. So this is kind of a famous formula, and here's a cool reason why it's famous. It incorporates the five most important constants in all of mathematics, are those namely pi, the ratio of a circle's circumference to its diameter, the natural number e, which is about 2.7 and comes up in all sorts of disparate areas of mathematics, I, the square root of -1, the imaginary number or complex number, and then the multiplicative identity 1 and the additive identity 0. So the five most important constants in all of mathematics are all in this single equation without any other constants, with no other numbers. So this equation really has had the fat trimmed in that it contains the most important numbers and nothing but the most important numbers. And it's not just the most important numbers, it's also the most important operations. So we've got the first most basic arithmetic operation of addition. We've got the second most basic arithmetic concept of multiplication. We've got the third most basic arithmetic concept of exponentiation. Finally, we have the fundamental equivalence relationship of mathematics, the equal sign. So, there's a whole lot that can be packed into this one single formula, and today I'm going to prove it to you. And in so doing, I'm actually going to prove a more general formula. So, to prove this formula, I will first prove the more general result, which is also sometimes called Euler's formula, which states that e to the ix is cosine x plus I times sine of x. Okay, and the method is going to be by way of Taylor series. So I will prove this formula using three known well-established Taylor series, and I'm not going to take the time to prove them here, although I could, but I'm going to take them for granted. So the three Taylor series that I will be using are very standard. So the first one would be, let's see, how about the e to the x series? So e to the x is 1 plus x squared over 2, or perhaps I should say 2 factorial, plus x cubed over 3 factorial, x to the fourth over 4 factorial, etc. So I could write this as the sum of x to the k over k factorial. The next known Taylor series I'll be using is sine, and the next one after that is cosine. So the series for sine is, let's see, it's all odd powers, alternating odd powers. So x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. Oh, did I do that one right? Yeah. So you could also write this more compactly as the sum of x to the 2k plus 1 over the factorial of 2k plus 1. Finally, we're going to need the cosine series. So cos x is only even powers of x. So x to the 0, x squared over 2 factorial, x to the fourth over 4 factorial, etc. So that could also be written more compactly as x to the 2k over 2k factorial. All right. So I'm going to take those formulas for granted, as I said, and I'm also going to use some easily established facts about powers of pi. Also, recall or note that, well, let's see. I to the 0 is obviously 1. Anything to the 0th power is always 1. I to the first power is just I. Anything to the first power is itself. I squared, by definition, is -1. I cubed, well, that's I times I squared, hence is negative I. I to the fourth is, well, negative I times I, which is negative 1 times negative 1, which is positive 1. Then I to the fifth, well, that's I times I to the fourth, hence it's just I. Wait a second. Notice a pattern here. So this term is the same as this term. This term is the same as this term. Want to guess what I to the sixth is going to be? And if you spotted the pattern and said, well, it's just going to be the next term in this sequence that repeats every four terms, you would be correct. It would indeed be negative 1, etc. All right. So now let's plug uh, ix in for x in the series for e to the x. So that would give us that e to the ix. Well, let's just take this series and replace all of the x's with ix's. Right? Apparently, it would be ix to the k, or using the first few terms written out, that would be, all right, so in place of x, I'm going to put ix. Okay, ix there, ix there, ix there. And you know what, let's write out a few more terms. So next we'll have ix to the fourth over 4 factorial. Next we would have ix to the fifth over 5 factorial, and I think that's enough terms. And now let's use these facts about powers of I. So this should be the same as, well, the first one will have an ix squared. Sorry, excuse me, I squared x squared. So I could write it as, oops, as I squared x squared, or I could just replace I squared with negative I. So let's just replace this with a negative 1. Okay, next term, we'll have a I cubed x cubed, but I cubed is negative I, so let's replace that with negative I. Next term, we'll have an I to the fourth, and I to the fourth is 1, so actually I can just ditch the I altogether. Next one would have an I to the fifth, which is the same as I. So it's just I x to the fifth. All right. So the next step is to group the real and imaginary parts, because the real parts are every other term. So those are those. Wait a second. Doesn't that remind you of this series? 1 minus x squared over 2 plus x to the fourth over 4. That's the same as that series. Okay? And the imaginary terms are the remaining every other term, the every other term that remains, and that should look like this series. We've got an x, an x cubed, a negative x cubed over 3 factorial, an x to the fifth over 5 factorial, etc. Oh, okay, pretty neat stuff. So, separating into real and imaginary parts, let's do the, how about the real parts first? So, here, I think I can just copy and paste this and delete the other term. That one, that one, delete that one. Okay, cool. So there's our real terms. And then let's pull an I out of the imaginary terms. And what will I have? I'll have an x. I'll have a minus x cubed over 3 factorial. I'll get a plus x to the fifth over 5 factorial, etc. Is it etc. or etc. or etc.? Etc. or etc. 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 All right. So In any event, as I pointed out, the real part here is exactly the cosine series. The imaginary part here is exactly the sine series. So this all then is the same as cos x plus I times sine x. Cool. So to recap, we've proved the more general form of Euler's formula, which is that e to the ix is cos x plus I times sine x, and that's a very important and general result on its own. But in particular, if we want to get the Euler's formula or the form of Euler's formula that I was talking about at the beginning of this video, well, what value of x do you think we should plug in? And if you said just take this one with x equal to pi, then you're doing good. So that's exactly what we're going to do. So let's let x equal to pi. In particular, if x equals pi, we get that e to the I pi is cos pi plus I sine pi. You may recall that I sine pi is zero, or excuse me, that sine pi is 0. So I sine pi is also 0. So we just get cos of pi. And you may recall that cos of pi is -1. So moving the -1 to the other side of the equation, we find that e to the I times pi plus 1 equals 0. Woohoo! The great result that was promised. Bum, bum, bum. All righty. Thanks for watching, folks. Hope. Hey, come on, get rid of that highlighter yellow. All right, there you go. Um, thanks for watching all that good stuff. Very impressive, very amazing. Mind equals blown, yada, yada, yada. Over and out.